Okay, we've been seeing some classic synchronization problems for quite a while now, and what we're going to be looking at right now is one of the most popular, most widely dealt with, and one of my personal favorite problems, one of the most interesting ones I believe you will encounter throughout this course. It's called the dining philosopher's problem. So, look at the diagram here. It's a round table, there are 5 chairs. We assume each chair is occupied by a philosopher. We have 5 philosophers. In front of each philosopher is a bowl of rice, and we have exactly five chopsticks placed on the table. So it is common knowledge that for any person to be able to eat, he or she needs 2 chopsticks. So the problem here is you want all 5 philosophers are going to be hungry at some point of time. Could be the same time, could be different time, whatever. When they are hungry, they need 2 chopsticks each to be able to use their rice. If each one happens to feel hungry at a different time, well and good. The first person uses 2 chopsticks, finishes their food, puts the chopsticks down. Then the second feels hungry, picks up the chopsticks, finishes food, puts them down. Then the third, so on and so forth, well and good, very smooth. But it is also possible that all 5 or even 2 adjacent philosophers feel hungry at the same time. Then this person also wants these 2 chopsticks. This person also wants these 2 chopsticks. Note that any philosopher can only take the 2 chopsticks which are adjacent to their bowl of rice. That is the one to his or her immediate left and immediate right. This person cannot reach for something across the table. That's one of the rules. So what if 2 or more people seated next to each other, or what if worst case all 5 people feel hungry at the same time and each of them picks up their left chopstick. So everyone has 1 chopstick in hand now, and they need another, so they can't eat. They have not eaten, so they will not put the chopstick down. Because they have not put it down, the next person cannot eat, so on and so forth. So it's a deadlock, right? We saw an example in one previous segment where there were 2 resources, I think S and Q, 2 processes P0, P1. P0 took S, P1 took Q. Now P0 needs Q, P1 needs S. Because each has 1, its job is not finished. It cannot put the claimed one down. It needs the other resource to finish the job. So neither is giving up, neither is moving. It's a deadlock situation. So that is exactly the idea of dining philosopher's problem. And how does this relate to computer science? Eating can be seen as analogous to some process, writing, updating something. Your chopsticks are the resources. If 2 processes need the same resource and one takes up this one takes up another one, it's going to be a deadlock. It is exactly what we saw in when I was talking about deadlock there. So that is the dining philosopher's problem. Now you can come up with a semaphore based solution for this. So it is possible. You can declare a semaphore variable array, chopstick of 5. So chopstick is an array with 5 entities representing the 5 philosophers, and each has a semaphore variable, and there are ways to solve this problem. So we're not going to go into that. I'll tell you why. But if you are interested, it's not too complicated. You can probably sit and work out a semaphore based solution, because we've already looked at a couple of semaphore based solutions for the previous problems. Anyhow, we are not going into the semaphore based solution for this problem, because any satisfactory solution to the dining philosopher's problem must guard against the possibility that one of the philosophers will starve to death. See, the thing here is, maybe this person first takes both and then they eat, then they put it down. Then this person takes both, they eat, they put it down. Again this person feels hungry, so they eat, they put the chopsticks down. Then this person, if this back and forth between this person and this person keeps happening, this philosopher is never going to get to access either of their chopsticks, so this person will starve to death, right? And in computer science terms, this process is never going to get any of the resources it needs. It will wait indefinitely, which is called starvation. And the thing about a semaphore based solution is, any semaphore can at max make sure that there is no deadlock. So you can use a semaphore based solution. You can do some of these things here, which I'm not going to go into in very detail, to ensure that deadlock does not happen. Everyone picking up 1 chopstick and hence being in a deadlock situation. That will not happen if you look at this semaphore based solution. So basically you're waiting for both chopsticks. Once you get both, you're eating, then you're releasing. That's the simple idea of a semaphore based solution. And I is the, let's say, your immediate left chopstick. I plus 1 mod 5 is your immediate right. Mod 5 because 1 2 3 4 5, and then it should not be 6, it should be 1 again. So for that, so basically this is the semaphore solution. It's very simple. Every philosopher has to wait to acquire access of both the left and right chopsticks, then you eat, then you release control, same thing. But the thing is, this can ensure that there is no deadlock. If you're not convinced, I would encourage you to take a pen and paper and work out any possible combination where one person is eating, the next person comes. Try it out, try out the weight and signal logic, which I'm sure you're familiar with by now. Deadlock will not happen, but there is no guarantee that starvation will not happen, and we want to avoid both deadlock and starvation. So we cannot be satisfied in this case with the semaphore based solution. We need to do better. So we go to something called the monitor based solution, which we'll look at in the next segment.